Welcome, everyone. Welcome to the last day of our virtual iOS conference. We already had two great talks, and we have another great one in store for you today. And it's my pleasure to introduce Professor Sam Burer, who is a George Daly professor in the Department of Business Analytics at the University of Iowa. His research mainly focuses on convex optimization, especially semi-definite and composite programming. He is, for instance, the 2020 recipient of the Informs Computing Paper Prize, and I'm sure that many of us are familiar with his work already. But his work has also been supported by grants from NSF, including a career award. Burer is already currently serving as an area editor in operations research, and as an associate editor, he's serving in SIAM Journal on Optimization, as well as he's currently the vice chair of the SIAM activity group on optimization. Today, he will talk about convexification for non-convex mixed integer quadratic programs, so these super difficult problem classes. And at the end of the talk, we will have a 10-minute Q&A session, but during the talk, as well as at the end, please feel free to post your questions or any comments, any thoughts on the Q&A tab, and we will go through that list together. And with that, Sam, please, the virtual floor is yours. Thank you so very much for joining us here today.
Thank you, Merve. Thank you to the organizers for the invitation to talk, and thanks to everyone out there in the ether who came to listen today. Yeah, I would like to talk about convexification today. I'm going to start with a very difficult problem, but I want to kind of zero in on particular substructures that appear in these types of problems and talk about how we can convexify that. I want to first thank my co-authors. This is joint work with Kurt Anstreicher at the University of Iowa, Anders Eldved at DTU in Copenhagen, and Kyung-Chen Park, who's a PhD student at the University of Iowa. So these are great co-authors, and I want to acknowledge their contributions. This talk definitely would not be possible without them. So let me get started and just jump right into the difficult problem that we'll be discussing. I'd like to basically minimize a general quadratic objective over general quadratic constraints, subject to bounds on the variables, and also subject to some of the variables being integer. The dimension here of the number of variables is n. So this vector x is a n-dimensional vector living in Rn. And I would like to try to solve this globally if at all possible. Now, we're going to abbreviate this today as MIQP, but you'll also see it in the literature abbreviated MIQCQP for quadratically constrained quadratic programming. And this really captures all sorts of applications. For example, if all of the all of the Hessians are 0, then you've got mixed integer linear programming. But it can also capture up to the class of polynomial optimization problems. So basically, if you give me a polynomial optimization problem using extra variables and constraints, a polynomial number of them, I can convert that polynomial program to an instance of this MIQP. So this is definitely an NP-hard problem. But the goal here, or at least the thing that we like to keep in our mind, is we would like to calculate a global optimal solution if at all possible. This is a good, interesting class of problems, though. I mean, for example, if you did have an unbounded set, we're going to assume bounded here, but if you did have an unbounded set, this is actually an undecidable class of problems as well. So there can't even be algorithms to decide what's going on at optimality for these problems if it's unbounded. But in the bounded case, we'll be able to solve this. Now, to actually solve it, we could, for example, do branch and bound. You could branch in the regular way on the integer variables, and you could do spatial branching on the continuous variables. And in particular, when you do this kind of implicit enumeration, what you'll want is some kind of convex relaxation at the nodes, which is the first area that I'm going to zoom in on. So what about a convex relaxation? Thinking about how we use convex relaxation when we're trying to solve these difficult problems, I think it's useful to think about mixed integer linear programming, the case when all of the HIs are equal to 0. What we can do in that case is get a very direct convex relaxation, an LP in the variable x, by just simply dropping the integer constraints. Likewise, if you have a convex MIQP, meaning that all of the HIs are positive semi-definite, then you can get an SOCP relaxation directly in X by just dropping the integer constraints. But just to highlight sort of the difficulty in this type of problem, if you try to do something similar, for example, you drop all of the integer integer constraints and try to get a relaxation, you're already in this general problem class, you're dealing with a non-convex relaxation that itself could be NP hard. So it's hard to, in some ways, it's hard to even get started with this problem with dealing with convex relaxations. Now, there has been a lot of work to do so. So this just gives you an idea of how it's a bit more challenging. I guess I maybe could go ahead and put a stake in the ground and say, well, what's the best that we could ever do here? What's the holy grail of convex relaxations in this case? What I've done here in the middle of this slide is essentially set up the exact same problem, but I've introduced an epigraph variable and I've moved the objective down into the constraints. And so the basic idea is that since we now have a linear objective over this non-convex constraint set, we could convexify the constraint set, and because that linear objective would then attain on one of the extreme points of the convex hole, that convexification would be a way to convexify this set. So I think it's probably fair to say that if we could magically come up with a convex hole, it would be this one. We'd want to convexify this feasible set in the variables x and t. Now this is going to be very difficult, but it does kind of give you an idea of where you're headed towards. Now, it also says that in general, we can focus on convexifying feasible sets because you can always move the objective down into the constraints. And so I'm going to not specifically name the epigraph variable, but I'm just going to think about, hey, can I convexify in the original variable x, can I convexify this feasible set? Or more generally, and this is going to be an important theme for today, can I introduce other variables and convexify in a higher dimensional space and somehow then project back down and somehow make the convexification easier. Now the standard treatment that I'll be using is basically an STP type treatment where you introduce a symmetric variable capital X, and that's equal to the vector X times its transpose. And this captures all of the quadratic terms, all of the xi times xj's, and then we convexify in the space of little x and big X. And that's the lifting piece. We convexify in this higher dimensional space, and then we can project back down to the X in order to capture this convex hole at the top. So these are sort of two different ways to think about it, and I just want to give them as examples right now, but essentially we'll be coming back to them over and over again also as we go through the talk. So the focus for today, though, is going to be really not so much on this general problem class, but rather on substructures that appear in these types of general MIQPs. And I'm going to present three different substructures that I've been working on with my co-authors. The first one is looking at bounded scalar variables, x, y, and z, just scalar variables x, y, and z, such that x times y is equal to z. Then I'm going to look at what I would call vector switching variables. You can also think of these as indicator constraints or maybe on-off constraints where you have a vector x and a vector y. The y is binary. And then you have these linear constraints, 0 less than or equal to x less than or equal to y. And the y essentially is each y is essentially a switch that turns on the x or off the x. If yj is equal to 0, then xj has to be 0. If yj is equal to 1, then x has the freedom to move between 0 and 1. And then the last substructure I'll be looking at is what I would call an extended trust region structure, where essentially you have this kind of donut sort of constraint. It says the norm of a vector x has to be between two radii, essentially a donut if you kind of graph it out. The norm on the x also has to be bounded above by a linear objective. This is an SOC constraint, second order cone constraint. And then we also have this bounded linear inequality, a two-sided linear inequality. In our research, we call this a slab. So basically, it's kind of the intersection of two parallel hyperplanes, and it looks sort of like a slab. And so we call that S transpose X bounded below by L and above by U to indicate that slab. So these particular substructures come up in a lot of different MIQPs, and I'll show you that as we go along. But that's going to be our focus, is to look at these substructures and try to understand better what's going on. Why do we focus on these substructures? It's basically, sometimes it's easier to focus on these simpler cases where you have fewer variables and fewer constraints. And these really can be the basis for then convexifying more complicated MIQPs. This is a standard technique, for example, that has been adopted in mixed integer linear program when you look at a one-row relaxation or a two-row relaxation, that sort of thing. So let me talk a little bit about the tools that we have in our toolbox. This problem class is very general, and so it's not really that surprising that there are a lot of different types of methods to convexify these problems. I'm going to suggest an overly simplistic, somewhat admittedly naive way to think about the tools at our disposal, and that'll help guide a little bit of our thought process. So basically, I want to think about making two decisions. If you need to convexify a problem, I want you to ask yourself, well, how many additional auxiliary variables am I willing to deal with? Am I willing to tolerate? The more auxiliary variables you have in your relaxation, essentially the bigger the relaxation will be. So there should be some kind of limit to what you can tolerate. But then you also have to ask yourself, what type of constraint constraint sets am I willing to deal with? Can I deal with linear programming, second order cone programming, or SDP? I know some people, love solving LP relaxations for very good reasons because the software is so well developed and so numerically reliable. SDP has very strong relaxations, but it can be harder to solve in practice. And SOCP is somewhere in the middle. So deciding on how many auxiliary variables we want and the type of constraint we want can really define the type of relaxation we're willing to deal with. And essentially, you can, in every box in this little decision grid, you can find some method that goes in there. For example, there are polynomial methods that are based on SDP, where they add polynomial number of additional variables. We're going to be focusing, the first example is going to fall in this quadrant or in this box, and then the last two are going to fall in the second box. One thing that's also kind of interesting, and maybe not so surprising, is a lot of times if you commit yourself to SOCP, then you might as well add in some linear constraints as well. It at least doesn't make the technology any more difficult. And same thing here, if you're willing to do SDP, then you're probably willing to do SOCP and LP as well. So this is the way I'd like to kind of think about it. And I'll give you some examples from the literature. This is very brief, of course. If you want to just stay in the X variable, for example, you can get convex underestimators in X using the alpha BB method. Buchheim and co-authors in 2013 also found ways to construct convex QP or SOCP relaxations if all of your variables are integer. There's a very popular method called a QCR method that builds a convex QP relaxation at the root node and branch and bound, which is gotten in order to strengthen the root node relaxation, but it's gotten by pre-solving an SDP. You don't solve SDPs everywhere in the branch and bound tree, but you can stay in the variable X and use SOCP. You can also add some auxiliary variables. Convex under and concave overestimators are gotten this way. For example, it's very common to add an extra auxiliary variable for each quadratic term, xi times xj. That's the McCormick inequalities. We'll see those in a couple of minutes as well. And then also you can also add in auxiliary variables, one for each quadratic. This is a little bit like the epigraph variable approach, where you add a t that deals with one quadratic at a time. And this appears in the work of Gunlock and co-authors and Beanstalk and Machalka, for example. You can also convexify the quadratics by using a difference of convex programming technique. And if you're in a separable case, all of your HIs are diagonal, all the Hessians are diagonal, then you can use piecewise linear approximation that has its own auxiliary variables, for example, binary variables and SOS constraints. There's also, now this is getting sort of into SDP territory, you can also use the lift and project paradigm for deriving LP and STP relaxations when you go from X transpose into X big X. That's Shirali, Adams, Balish, Saria, Konerjols, Lavash, and Schreiber. There's disjunctive approaches that derive cutting planes into little x and the big X and also project them back into the little x. There's also cutting planes that really just look at the lattice structure of the integer points. You can actually take an STP relaxation and further relax it as an SOCP or an LP, and there are some results dating back from the 2000s, early 2000s, and that's been refreshed more recently. And then if you want to go kind of full power, you can do polynomial approaches, and this is the moment approaches and the sum of squares approaches by Lasserre and Perillo. So there's really lots of things that you can do here. Now, again, what I would like to do is focus on these substructures. And so let me start with the case of z is equal to xy. So my ground set here is going to be the box, a non-negative box in 3 dimensions. So I'm going to start for the beginning here, saying that x and y are 2 variables that are bounded between 0 and 1. And then z is a third variable that's bounded between L and U. Now, L and U can really be anything. I'm going to specify different cases of what they can be in just a moment, but basically think about them as just non-negative bounds on the Z. And what we'd like to do is convexify the box intersected with this quadratic surface, z is equal to x, y. And I'm going to call that CH for convex hole. And in fact, I'll use that CH. Anytime you see CH today, it means convex hole. So we'd like to get this convex hole, and I'm only going to deal with these three variables. I don't want to go up into higher dimensions or anything. I just want to stay in there and see if I can convexify this. This kind of these kind of terms and this kind of convexification is relevant anytime that you have a product of two variables in an MIQP. And it comes up, I already mentioned the McCormick inequalities. It comes up in a lot of different cases. If you have specific bounds on the z variable, this particular case has been studied by Belotti and co-authors. They fully characterize the convex hole using an infinite class of so-called lifted tangent inequalities. These are linear inequalities that have something to do with a tangent on the surface of the xy equals z surface. Wen and co-authors also derive the convex hole using a more general framework where they look at z is equal to the product of x to the a, y to the b, where the exponents a and b are greater than or equal to 1. Now, the results that I'll show you today are actually contained in the results of Wen and co-authors, but their formulas assume that the bounds below on x and y are 1, and they leave the case going to 0 where you have 0 bounds. They leave that to a scaling and a limiting argument. And so their formulas actually aren't very easily compared with the ones that I'll show you. They also, what we did is we just focused on the a and the b equal the exponents being 1, and it allowed us a more straightforward derivation of what you'll see. Another thing, another recent work, Santana and Day showed that the CH that we're dealing with is actually SOC representable by using a disjunctive representation in a lifted space. So actually adding more variables and doing a disjunction convexification there. But we would like to stay in this lower dimensional space, and we're actually going to show that things are SOC representable. And that in fact is the main result for this convex hole. The convex hole is SOC representable with no more than 3 SOC constraints, and they're explicitly given. We can write them down. And basically what we do to prove this is just revisit this infinite class of lifted tangent inequalities and show that the SOC constraints that I'll show you in a moment can capture these exactly. So let me show you how this kind of works out. So to touch back with some of the known literature, assume that the bounds on z are 0 and 1. This is what we would call the trivial bounds because they aren't any tighter than what would already be implied by the bounds on x and y. And McCormick showed in 1976 that essentially you needed these McCormick inequalities, which I'll call RLT here, and those are defined here. It's basically everything that's in the box with these 4 inequalities. And this is gotten in different ways, but essentially I want to focus on this idea of reformulation linearization technique that was introduced by Shirali and Adams, where you take linear inequalities that are valid, you multiply them, and then you get a quadratic inequality, which is then linearized. And so McCormick basically said, if you want to be just z between 0 and 1, then you just need these McCormick inequalities. And the picture looks something like this. The box is shown as the frame of reference here, x, y, and z. And the surface, x, y equal to z, is the 3-dimensional surface that you see. And the red lines are the convex hole. So this is basically a 4-sided polytope where the 4 sides are defined by the facet inequalities that you saw on the previous slide. So this is what was known. Now, if you decide to tighten the upper bound on u just a little bit and make it a less than 1, then what we were able to show is that all of those lifted tangent inequalities that were already known can be summarized as this one inequality. So the convex hole is the same RLT intersected with this one quadratic inequality, z squared less than or equal to u times xy. And this inequality is SOC representable. It can be represented easily using a rotated second order cone. And so bringing that bound just down a little bit, you get the convex hole here. Let me show you a picture of that. So this is like the previous picture, except in the z dimension, we cut it at 0.4. And what that does is it kind of ruins the polyhedral nature of the convex hole. You can still see the dotted line, which is the outside of the RLT, but to actually capture the surface, you need this green curved piece, and that is exactly the second order cone constraint. Now, if you decide to reset the upper bound on u to be 1, upper bound on z to be 1, and then you tighten the lower bound to be slightly positive, a little bit L is positive, This is what we would call a non-trivial lower bound on Z. Then you can prove that the convex hole is just RLT intersected with another second order cone constraint, which you see here. It's not completely obvious that this is a second order cone representable at first, but it turns out that this Hessian here that you see is positive semi-definite. And so you can see that this is just the norm of a particular linear vector. And so this is SOC representable, and it's able to capture the convex hole. So this is what the picture looks like for this case. You chop the Z from below, and then everything above is now captured by this curved region, this curved yellow region. You still do need some of the RLT that's kind of on the back side here, but the other RLT that's more on the front side has been dominated by the SOC constraint. Now, as a quick application, one thing that you might think to do in spatial branch and bound, a lot of times people will often branch on the X and the Y. One thing you could do is maybe think about branching on the Z now. So imagine you have an MIQP that has bounded XY in 0, 1, and then it has this, this relationship Z is equal to XY like we're talking about, but then you have trivial bounds, at least at the root node, you have trivial bounds on the Z. So one thing you could imagine is doing spatial branching on the Z, where you chop the Z in the left branch, you say that it's between 0 and a particular bound, and then on the right branch, you say it's between the bound and 1. And then you could enforce this convex hole in each of the branches, the two convex holes that I've shown you. And the question is, what's the volume reduction compared to just enforcing RLT? Part of the reason we branch is so that the size of the feasible sets gets sort of cut in half or cut in two. And if you could branch in such a way that the total volume in the branches, the feasible sets of the branches were relatively small or as small as possible, that could be a good computational strategy. And so what I'm basically saying here is, imagine you have the original picture, but you decide to cut it right in the middle of this case where we're branching at Z is 0.3, and then convexify in each of the branches, in this case, sort of the bottom and the top. And the question is, what is the volume of the resulting object relative to what you would get if you just did RLT, which are the dotted lines that are remaining here? And what we have here is kind of a summary of that analysis. And I think I'll just show you the red curve or talk about the red curve. So the red curve basically gives you the percentage volume relative to just doing RLT if you branch at the point or branch on the bound according listed in the x-axis. And what you can see essentially here is that at around 0.2, if you branch Z is less than or equal to 0.2 and Z is greater than or equal to 0.2, if you branch right around there, then you get a little over a 30% reduction in the volume compared to just doing RLT, counting both branches as summing both the volume in both branches. And so it gives you an idea that maybe, for example, branching at 0.5 is not such a great idea, but branching around 0.2 is a much better idea in terms of the volume of the resulting feasible sets in the two problems you create. Now let me talk a little bit about non-trivial bounds on Z. So imagine you have L is positive and U is less than 1. Then what we can show is that the convex hole is RLT intersected with three SOC constraints, each of which is applicable on a particular domain of XY values. Now, looking at this geometrically, we think of this as the center part of the region, and this is one side, and this is the other side. And so what we have are two side inequalities and one center inequality. The two side inequalities are similar, but they sort of switch the Y and the X. There's a little bit of symmetry going on. And down here, these are the explicit formulas for the center and the side inequalities. And these are essentially just versions of things that I've already shown you, but because we've now imposed non-trivial bounds in the L and the U, we now have them all coming together. But these are only applicable on certain subdomains. And it looks something like this. Now this picture is, for example, you're cutting at about 0.2 and 0.7. Z is less than or equal to 0.7 and greater than or equal to 0.2. The green is the center constraint. The yellow here towards the front of the picture is one of the side constraints. And around the back, which you can just barely see, that's the other side constraint. And that's the convex hole in this case. Now, one thing that's kind of interesting is that you can prove that the center constraint is globally valid, but the side constraints are not. So actually, one interesting thing that we thought about is, what if you just put in the center constraint as a global constraint and really don't even maybe worry about the side constraints? And what we found is that if you do so this is what the exact convex hole looks like, and this is what it looks like if you just release the side constraints, you don't enforce those, and you only have the center constraint, then you actually get a very nice, empirically, you get a very nice approximation of the convex hole. So it's amazing how little the side constraints are actually cutting off. Said differently, the center constraint could be enough in practice just enforcing that, and it's globally valid, so you could just put it in and not really worry about it. You wouldn't have to sort of splice based on the part of the domain you're in. Now, there are a couple of, one main extension I want to give. So I have been assuming that the bounds on X and Y are between 0 and 1. But if you do have general non-negative bounds, then we can also prove that the convex hole is characterized by the RLT constraints. You do have to include the bounds on Z. And then up to 3 SOC constraints, each of which is applicable on a subset of the domain. So it's essentially the same result, but there are sort of different cases that you have to look at, and some of the functions, SOC constraints, change form a little bit or change some of their coefficients, but it's essentially the same idea as what I've shown you. So that is the first application, understanding what's happening with these 3 variables. Now I'd like to kind of switch gears and talk about what happens in the case of having more of an n-dimensional set and looking at these so-called switching or on-off or indicator variables. I'm going to call the set that we're really interested in the Switchbox set, Switchbox subscript n. And it's a set of all vectors x, y, both of size n, such that 0 is less than or equal to x, less than or equal to y, where y is a binary, y can be turned on or off. Now this is a space existing in dimension 2n. And what we would like to convexify is get this convex hole subscript n. It's the convexification in x, y, and big X, where x and y are in the switchbox, and big X is equal to little xx transpose. Now, what this will allow us to do is allow us to capture anything quadratic in those variables in X. But you'll notice that I'm not trying to convexify in the quadratic Y or in the yi times yj. I'm not also trying to convexify in yi times xj. So I don't have those cross-term matrices. I'm just trying to convexify in the quadratic in X. Now, I mention this because these cross terms are actually going to come back in a moment. They actually will allow us to prove something that that helps us get this convex hole, but doesn't actually relate directly to the convex hole. So the cross terms are actually going to be important. This type of problem comes up in quadratic problem comes up in a lot of different areas that you can see here: electrical power production, portfolio optimization, nonlinear machine scheduling, chemical pooling problems. And most of the computational experience has used just CH1. So looking at an X1 and a Y1 that are the switching variables. So sort of the simplest dimension. And a lot of good computational work has been achieved by just looking at that one case. Let me mention what that convex hole is. CH1 is just this convex hole in 3 dimensions, where you have all the basic linear bounds on the variables. And then you have this one nonlinear constraint, x1 squared less than or equal to x11 times y1. And this is called a perspective constraint. It's SOC representable, and it's been very critical for understanding this convex hole and then being used in applications as well. So this was developed in 2010 by Oktay and Jeff, but there was also some prior work by Frangioni and Gentile as well. So it is known what CH1 is. And people have tried to look at the general case. What are some valid inequalities for general n? For example, Hongbo Dong and Jeff Linderoth did that in 2013. What I'd like to do today, though, is talk about CH2. So I just want to go up to 2 variables and see if we can understand that convex hole a little bit better. So that case also has been studied. It's been studied by Gion and others in 2017, and also Frangioni in 2020. The convex hole, this convex hole, a related convex hole, has been studied by a number of people as well, most recently by Han and co-authors, where they essentially look at what happens if you have a convex quadratic function over these switching variables and you look at its epigraph and you try to convexify that. One interesting thing that differs in their research is they didn't really worry about the upper bounds on X. So they basically just turned X off with the Y variable, but X could be have an unlimited upper bound in that case. So our goal, though, is to look at CH2 and just try to understand, can we fully characterize what CH2 is? So let's take a look at that case a little more carefully. I've got a little schematic here on the right side of the slide that shows basically what's going on with n equals 2. Let me focus your attention first on the y. Now the y is binary, and I've shown you the 4 different options of the y vector. It's a 2-dimensional vector, and I've kind of plotted it on the unit box. So this is just meant to be, for example, y can be 0, 0, or it can be 1, 0, or it can be 0, 1, or it can be 1, 1. Now, for each choice of those y's, we then get a resulting choice, we get a resulting feasible set for x. So if y is 0, 0, then x is 0, 0. It's completely turned off. If y is 1, 0, then x1 can range between 0 and 1, but x2 has to be 0. This is the third case is kind of the flip of the second case. And then in the fourth case, when y is 1, 1, then you have full flexibility for the x to go around in this unit box. So you can think about Switchbox 2, the n equals 2 case, as the union of 4 sets. And so it's the convex hole that we want is actually the union of 4 convex holes. And those 4 convex holes, we actually know them, and I'll show you on the next slide. So in principle, what we could do right now is just say, okay, well, the convex hole 2, CH2, is just the union of 4 convex holes. So let me just do a disjunctive formulation, add some few auxiliary variables, add that in and be done with it. That is certainly reasonable, and it will give you the convex hole. But we'd like to try a different approach. We'd like to get an approach that hopefully gives us a little more insight into what's, well, sort of really going on here. I mean, you'll have to see if in the final version you think, hey, does that give us some insight? I think so. I think you'll agree. It gives more insight than just doing the disjunction. But this disjunction is a possibility. We'll go this different route. So I just mentioned that for these 4 cases, if you consider that y is fixed, for those 4 cases, we know what the convex hole is, and that is true. So if the y is 0, 0, we just have a singleton. The convex hole of that is just going to be a singleton. When you have either y is 0, 1 or 1, 0, you're essentially back in the 1-dimensional case. So you essentially have just a kind of a copy of CH1. And then if you have the case that y is equal to 1, 1, and x can range over the box, then you have a result by Kurt and me from 2010, where we basically proved that the convex hole in the x's is enforced by just taking an SDP constraint and enforcing RLT, basically those McCormick inequalities that we've now seen a couple of times. And this gives us an idea that, well, maybe there's something going, maybe we can get some additional insight because we know these 4 pieces. Maybe we can kind of figure out then if we convexify this and the y is not fixed anymore, then we can figure out a good understanding of that convex hole. And that's kind of where our starting point was to think about this research. So again, this is the convex hole I've already stated. This is what we would like to get in the x, the little x, the little y, and the big X. But to get the proof going, or to get these new concepts of our contributions going, what I would like to do is now bring back or include those cross terms that I mentioned earlier had been excluded. So what I'm going to do is basically, I'm going to introduce a new convex hole, which is in a higher dimensional space, CHN cross. It's got the same x, y, and big X, but we're going to introduce a big Y and a big Z, where y is the little y, y transpose, and big Z is little y times X transpose. So essentially, we're going up into a higher dimensional space, and we're going to try to convexify there and understand what's going on. We can always then project back and get the convex hole that we really care about by just doing a projection. Now, when you take this approach, you can now think about validating inequalities for general n. And so you can, for example, you have a standard SDP approach. So we can add this SDP constraint. This would be a 2n plus 1 by 2n plus 1 SDP constraint. You can also do RLT, like I've been talking about. So you can do RLT with all of the x's. You can do RLT with all of the y's. And I'm going to go ahead and overload the RLT notation here a little bit. And I'm actually going to include some additional constraints that aren't necessarily thought of as RLT, but I think they fit, at least in the terms that they're linear. That you can also constrain the diagonal of big X to be less than or equal to X. This represents the fact that the Xi variable is between 0 and 1. We can go ahead and throw in the switchbox constraint that X is less than or equal to Y. And then also, we can express the binary nature of Y by saying that the diagonal of big Y is equal to little y. So I'm going to throw those all into the set that we call RLT. And what Kurt and I proved, and this was really just reproving some results from the literature, we found out that the CH1 cross set is just SDP intersected with RLT. So essentially, if you look at n is equal to 1 and you just care about one switching pair, then if you go up into the higher dimensional space, CH1 cross is just STP and RLT. And so that immediately led us to a question, well, maybe CH2 cross, remember we're really interested in the case n equals 2, maybe CH2 cross is just STP intersected with RLT. And that turns out to be false. So you can just exhibit some counterexamples to show that CH2 cross is properly contained in the STP intersect RLT. But, and this is where I think it gets interesting, we did a lot of computational experiments and we came up with a conjecture essentially that even though CH2 cross is properly contained in the intersection of SDP and RLT, if you project back, if you project down to the space we really care about, the projection of SDP and RLT is the same CH2 that we really care about. So when it comes to really dealing in the original and in the variables we care about, the little x, little y, and big X, we can get CH2 by just projecting down this SDP RLT from the higher dimensional cross terms. I'll come back to this conjecture in just a moment as well. Now, what we were able to prove, actually, we were not able to prove this conjecture, but what we were able to prove is the following. So we recall that the semi-definiteness arises by relaxing this rank 1 matrix, outer product matrix, into this bigger SDP matrix. That's a pretty standard approach, and this is what it looks like for n equals 2. You get a 5 by 5 positive semi-definite matrix. Now for Switchbox, in the particular case of Switchbox 2, we also have what I consider to be a fairly surprising result, that if you take this quadratic vector and you take its outer product with itself, you get something that's positive semi-definite. And because you have something that's quadratic times quadratic, you would think it would be quartic. The result would be quartic, but actually you get, you can then realize that the resulting matrix is quadratic in the original variables because of the special nature of Switchbox, and then you can then linearize it in the variables that I've introduced. For example, you have the little x variables, the big X variables, you have the big Y12 variable, the big Z12 variable, and it turns out that this SDP condition, this linear matrix inequality in those variables, it turns out that this is actually stronger than the normal SDP condition. And so what we proved is that this new SDP condition, which we'll call SDP plus, actually strengthens the regular SDP condition. And moreover, that's exactly what you need to capture CH2 cross, so the convex hole in this cross term higher dimension. And then it follows that the convex hole that what we really care about is just the projection of SDP plus intersected with RLT. I want to mention the proof technique here a little bit because this turned out to be, even proving this theorem, not even, we haven't even gotten to that conjecture, unfortunately, we weren't able to prove that conjecture, but just getting to this theorem turned out to be a lot of work. We actually started with the disjunctive formulation that I was mentioning earlier. We were able to eliminate some variables that resulted in more PSD conditions. We were able to show that those PSD conditions were redundant in some sense. And essentially, we went through kind of this sequence of logic to get down to this result. There's got to be a way to simplify the proof. We don't know what it is at this point yet. Now, let me mention the conjecture again, and this will be kind of finishing up on the Switchbox example. The conjecture that we have essentially is that even though we need SDP plus for getting the convex hole with the cross terms, we actually don't need it when we ignore the cross terms. So even though it's necessary in the higher dimension, it's not necessary in the lower dimension. And what this would basically say is that SDP RLT, that basic idea is still very powerful even in the Switchbox case. It comes up a lot, and SDP RLT is usually a very good relaxation in a lot of cases, and it even extends to this Switchbox case that has binary and continuous variables simultaneously. So this conjecture is still to be proven. Hopefully we can simplify the analysis and it'll make the conjecture easier to establish. Now, in the last example for today, I'd like to talk about an extended trust region problem. And I want to first give the motivation for this, the reason Anders and I even got into this research. So Anders is in his PhD thesis has been working on the alternating current optimal power flow problem, which as a lot of people in our field have been working on lately. And in particular, we were interested in the result of Chen, Atamturk, and Oren in 2017, where they looked at a particular substructure that appears in the ACOPF problem. And the way they formulated it, I actually used their exact notation here, is they said what they would like is to look at this four-dimensional set with these variables, the W's and the T's. And they wanted to look at the convexification of several linear inequalities, as well as one quadratic equality, and convexify that in R4. And that turns out to be very relevant for a substructure that appears a quadratic number of times in the ACOPF. And so getting the convex hole allowed them to generate some constraints, which they could then use computationally. There are some basic assumptions on the data here. I won't go through those, but essentially those are natural in the ACOPF. And what they showed is that they could get the convex hole by essentially just doing two things. First, relaxing the quadratic equation to a quadratic inequality, which is convex QP. And then they said essentially that you also have to enforce two additional linear cuts. And those cuts are given here. Again, I'm just using the notation directly from their paper. You can see the variables, the W's and the T. Everything else is a constant based on the data, the L, the capital L and the capital U. Now, you have also these constants, these coefficients pi's that are depending on the L and the U. I'd like to show you that on the next slide. The pi's do have explicit formulas. You can just write them down. They're not particularly, they're easy enough to write down, easy enough to program. To me, they don't instantaneously tell you where are these numbers coming from and what's really going on. And that's where our motivation came from, is can we understand these cuts that they came up with? Can we understand them a bit more generally? And so that got us investigating what was going on. And what we realized is that the JC that they proposed is really just a simple projection of this convex hole where you have X and big X. The little x comes from R3, and it satisfies certain constraints. It satisfies a donut constraint. The norm of x1 and x2 are between bounds. And it also, the norm of x1, x2 is less than or equal to linear function in x1 and x2. And then you have simple bounds. You have a two-sided inequality on x3. So if you could convexify this, then you just do a very simple projection and you get the JC that they were studying. Now the B here is data that also depends on the L and the U. It has a particular form that's gotten by solving this little 2x2 linear system. Now, just to show you the geometry here a little bit, if I take the set that I just showed you, what we're essentially dealing with in the x1, x2, we're dealing with the intersection of a donut and a polyhedral set that emanates from 0. That's essentially what the norm constraint less than or equal to b1 x1 plus b2 x2 means in this case. And so essentially the feasible region in x1, 2 is just the sector of a donut. And then you cross it in this case with a linear, with an interval in x3. So what that got us thinking about is, can this be generalized? And we realized that it really looks sort of like a truss region type problem, where you convexify a donut constraint, you have a linear bound on the norm, and then you have what I called earlier a slab constraint, a two-sided inequality on S transpose X. And we would like to convexify this. Now, I want to mention that if you're dealing with quadratic objectives over this set, then it's known from Beanstalk that you can solve this quadratic objectives over this in polynomial time. But we're interested in tight convex relaxations, and Dan's techniques for this don't really involve the convex relaxations. So we are interested more in kind of understanding what's going on in this convex hole. So you can start to do a bunch of different things. You can do what's called the shore relaxation, which is basically, hey, just do a standard STP relaxation. For example, this first constraint is the donut constraint relaxed to the big X space. This is the norm constraint. Here's the STP condition. You can certainly do a standard STP trick. You can also add in RLT, where you take two non-negative quantities, in this case coming from the slab, you multiply them, and then you linearize to get a new linear cut in the lifted space. You can also do something that's called SOC RLT, where you take an SOC constraint and you multiply it on the left and the right by a non-negative quantity. In this case, I've represented that as U minus S transpose X. And you can then linearize that and you get an SOC constraint in the little x and the big X. This first appeared in Sturm and Zhang in 2003. You can also do something that's even more powerful, and that's called the Chronicler SOC. And this was introduced by Kurt a few years back, where essentially you reformulate, you recast any SOC constraint as an STP constraint. And then if you have two of those, you do the Chronicler product of them together. The Chronicler product of PSD matrices is PSD. And so then you get something that is quadratic PSD, which can then be linearized. And I haven't written that down completely in this case, but here are the two SDP matrices that we take the Chronicler of to get an even stronger constraint. Now, with a little bit of tongue-in-cheek, I want to call this the kitchen sink. So I've just introduced a bunch of different types of relaxations or valid inequalities. Let's call that the kitchen sink. You can add short relaxation, all possible RLT cuts, all possible SOC RLT cuts, and also this Chronicler SOC constraint. You can actually prove some relationships between these different inequalities, but let's just put them all in and call it the kitchen sink. It turns out that the kitchen sink does not capture the convex hole, even if the dimension is equal to 2. So there's still something missing. And this is where Anders and I really started to try to derive something new. What we did is we took all the ingredients in the feasible set. You can see all 5 ingredients here. We've got the lower bound on the norm, the upper bound on the norm, the linear bound on the norm, and then you've got those 2 inequalities on the S transpose X. And we said, well, let's see if we can combine these ingredients in different ways. And what we did first is we essentially, we took Rx, which is in the second order cone, and B transpose X, X, which is in the second order cone, and we pre-multiply them by non-negative scalars, S transpose X minus L and U minus S transpose X. This kind of idea comes up in polynomial optimization where you use polynomials as non-negative polynomials as multipliers to keep you in a cone. And essentially that's what we're applying here, but in a very specific case. So we can see that this quadratic expression is in the second order cone. Likewise, you can do something that's kind of similar to RLT using these 2 bounds. You multiply 2 non-negative quantities, you sort of rearrange, and you get this nonlinear expression, which is in the second order cone. Now you have 2 new things that are in the second order cone, and because they're in the second order cone and the second order cone is self-dual, you dot them and you rearrange. And what's nice is that certain terms cancel out just perfectly, so that essentially you get this new quadratic inequality in the little x, which can then be linearized, and you get this new cut in that you can add to the kitchen sink. And in fact, what you can do is you can use different multipliers. So not just the S transpose X minus L and the U minus S transpose X, you can use different multipliers. And as long as they're non-negative over a certain set, then you can use those. And what we proved is that this class of new linear cuts can be separated in polynomial time, more precisely epsilon separated. And the cuts do in fact strengthen the kitchen sink. So that was despite all of the power of all the kitchen sink things, you can here get something new by arranging the ingredients in a particular way. And then what we did is we looked back at those ACOPF cuts, and it turns out that you can just work out on paper that these cuts that were introduced by Chen and co-authors are essentially members of our class. And so that was the sort of the result of the research, at least in our minds, is that we wondered, was there some way to think about these cuts a bit more generally? And this is this is the answer, because all of the pi 0, pi 1, all these weird coefficients work out very nicely. Now, I want to mention one other quick application, and then we'll be wrapping up, getting towards the end. Another application of this technology, of this extended trust region technology, is the convex hole of essentially a set that I call the non-negative ball. You have a bound on the norm of your vector variable x, and you also want your x to be non-negative. So you could think about this as a substructure that comes up anytime you have non-negative variables and some kind of norm bound, Euclidean norm bound on them. And so if I want to convexify that, I can think about it in different ways. One of the things, the first thing I'm going to do here is add an infinite number of redundant slab inequalities. So I probably should have drawn a picture just to show you this, but if you give me, essentially, if you have the non-negative ball, which is a little sector of the ball, and you take any unit vector, then you can prove that the unit vector its minimum value over that non-negative ball is 0 and its maximum value is 1. So I'm going to add that infinite class of slab inequalities. And then what I'm going to do is I'm going to use the fact that the 1 norm is greater than or equal to the 2 norm in order and especially on non-negativity, to include this constraint that the norm is less than or equal to E transpose X. And so now down here, you have an instance of our extended trust region subproblem. Now we've actually relaxed a little bit here. So we've gotten away from our original convex hull, but it does hold with equality for dimension 2. And what you can do here is apply this technology with these linear inequalities and these slabs. And actually what you can do is optimize over the S and get the strongest inequalities possible. And we have this corresponding theorem that says essentially, if you give me a partition of the variables, an IJ partition of the variables, and you define a certain domain where this vector capital X times E minus X is either non-negative, or it's non-positive on these certain entries, then locally on those domains, the SOC constraints you see here are valid. And so essentially what we get is this, it's really 2 to the n sort of valid constraints that are locally valid on these different domains. And they're second order constraints, because what we did is we took all of these linear constraints and we found the optimal S, and the optimal S would actually turn into an SOC representation. Now, we do have a conjecture for this non-negative ball. So for n equals 2, we think that if you take the non-negative ball, you put in the kitchen sink, and you also put in all of these locally valid cuts that I just mentioned, then you actually capture the convex hole. Now, this conjecture, again, it's for dimension 2, so it seems small, but we're just trying to prove what we can in small dimensions to give us an idea of how strong these inequalities are and how valuable they could be in computation. Now we can do some extensions here. I'll mention just briefly that essentially we can extend all of this to a general second order cone set where you intersect a donut with a general second order cone, and you can get similar types of linear cuts. I think I'm ready to give my conclusions. Thank you for sticking with me all the way to the end here. I guess my main point is that we really have a lot of choices when we convexify in MIQP. We've got to decide how many additional variables we're willing to deal with, what types of constraints we're going to allow in our relaxations, and then what substructures we want to focus on. And I've shown you today 3 important substructures of different types that show up in different applications. But I think also important are these themes that keep popping up. For example, we've seen several times that second order cone constraints come up because they represent an infinite class of linear inequalities. We saw that the SDP RLT was very important. It's a very basic structure in this type of approach. But we also have things like the SOC RLT and the Chronicler SOC, which can strengthen those. And in general, there's always going to be the availability of exploiting the structure that you have on hand in your problem to derive valid constraints. And that's what we did with the extended trust region. There really is tons to explore here. There's going to be plenty for all of us to work on for many years to come. And so I hope this talk is giving you some insight into this research area and optimization. Thank you so much.
Thank you very much, Sam, for the great talk. And thank you very much, everyone, for attending. So if you have any questions, please feel free to post them on the Q&A screen, and we will be happy to answer them. We still have some time. Now, personally, I'm very much intrigued by the conjecture. And yeah, I will be very curious to see whether SDP intersected with RLT is actually projection will give you the C2. Okay, so we have a question. Can you please speak about the computational challenges with working with piecewise valid inequalities?
Yeah, so something like this where you have piecewise valid inequalities, and we saw them also in the bounded XYZ case. My understanding is the most common approach essentially is that you would use these in a separation procedure. So you wouldn't enforce them in your first relaxation, but once you solve the relaxation, then you would look for one of these domains and one of these constraints which was violated. And then you could generate a linear inequality that supports that place and cuts off your solution that doesn't satisfy them, and then adding in the linear inequality that would be globally valid. And so you would just enforce these essentially as linear inequalities locally, which then become global because they're linear. I think that's the most common computational technique, but it's very nice to have this sort of compact representation, because then at least you know kind of geometrically what's happening in all of these regions.
Thank you. Any other questions? Maybe not. All right, so then with that, on behalf of the Optimization Society, I would like to thank our amazing speakers as well as all the participants for attending. And I hope you enjoyed this brief conference, and we are looking forward to seeing each other next year in person, hopefully in the actual conference. Thank you so very much again, Sam.
Thank you.
It's been great.